They become interesting only if certain things are true that are not maybe entirely proved yet. So we'll see how. Well, you'll see as we get there. Okay, so let me start with a brief introduction on imaginaries, because they'll be the core topic of our talk. And so mostly I'm not so much interested in imaginaries as in eliminating them. So the elimination of imaginaries is the question of finding moduli spaces for definable families of definable sets. And so I'm not going to exactly present it this way, because it will be more practical for me to present it slightly differently. And you might even think that I'm presenting it in a completely backwards way, because I'm actually defining first what an imaginary is and then explaining how to eliminate it. So let me get into what this EQ thing is, which is adding all the imaginaries. So if you start with an L theory T, you can define the following language LEQ, which is a language where you forcibly add moduli spaces for definable families of definable sets. So you add a new sort, which will be interpreted as the moduli space, and you add a function f, which is going to give us the point corresponding to the fiber in the moduli space. And then you write a theory T that says that you've done exactly that. So you write a theory T that says that f of x induces a bijection between E of x, the sort we added, and y quotiented by having the same fiber. Okay, so that's the EQ. And since it's very close to being a definable expansion, in a sense it is a definable expansion, any model of T has a unique LEQ enrichment MEQ, which is a model of TEQ, and conversely every model of TEQ is of the form MEQ, so for some model of M, for some model of T. Okay, so now we have all the definitions to be able to understand the statement here. So essentially what the statement here says, so let's forget about D, and if you want, take D to just be your home sort. What the statement says here is whenever I have an imaginary, I can find a tuple that I really understand, such that these two things are interdefinable, and so for all intents and purposes, I could replace E by D in everything I do. And so in this way, since E is probably encoding some point in a definable family, then D is going to play that role from now on. So why do I have this big D around? It's because, well, in most of what I'm going to do, the theories do not eliminate imaginaries in the home sort, and you do have to add a few interpretable sets so that you can eliminate imaginaries. So by an interpretable set, I just mean a set definable in TEQ. Okay, so that's elimination of imaginaries. So let me define a few more notations that I will be using throughout the talk. So sometimes I don't want to take all imaginaries for the whole theory, and I just want to take those that live inside a certain collection of sets. So if I take D, stably embedded a definable collection of sets, so you can mostly ignore stable embeddedness. It's just to make sure that the A-induced structure does what I want it to do. And then I will denote by DEQ the collection of imaginaries that you get on the structure induced by A on D. And also, I will be using this notation a lot. So if X is a definable set, it has a smallest definably closed set of definition that I will call corner X in MEQ. And actually, having a smallest definable set of definition is another possible definition of elimination of imaginaries. Okay. One last thing, which is that, well, I'm not really going to talk about elimination of imaginaries in this talk, because most of the time, elimination of imaginaries can be split up in two distinct parts. First, proving what's called weak elimination of imaginaries, that I'm going to define in a second, and then doing what you need to go from weak elimination to elimination of imaginaries, which is to encode finite sets. So today I'm not going to talk at all about finite sets, because most of the time it's an entirely different question. What I'm going to do, though, is prove weak elimination of imaginaries, which is that instead of finding a tuple, which really you can replace it, can replace E by, you only do it up to ACL in one direction. So D is algebraic over E, but E is definable over D. So if you know D, you know E, but the other way is not quite true. You have a finite cover around. So if you rephrase that in geometric terms, so this tells you that every definable every definable family of definable sets has a definable moduli space, And this tells you that you can find a finite cover of the moduli space, a definable finite cover of the moduli space. Okay, so hopefully now we all know what I'm going to talk about. And so now we'll move on and try to look at what happens in the valued field. So as I told you, if you take a valued field and you do what most people have been doing in this conference, which is look at it in the field sort, there is no hope to eliminate imaginaries. Right? The first culprit is, if I can find my pointer, yes. The first culprit is gamma, because there is an easy cardinality argument which shows that it cannot be in definable bijection with a subset of the field itself. Similarly, the residue field can be, as you probably guessed by now, I will, whenever I have a valued field K, I will write O for its valuation ring and M for its maximal ideal. And yes, so little k also causes essentially the same problems, which is that, there are cardinality issues. And in fact, more generally, you can consider higher dimension versions of these things that also create troubles. So this set here is actually appears elsewhere in the literature. It's the moduli space of lattices of Kn. That is free rank n, O submodules of Kn. And why is it this set? Because it's essentially given by choosing a basis, and two bases give you the same lattice if they're conjugated by GLNO. And so why do I say that this is a higher dimension version of gamma? Well, because if you look at it, S1 is exactly gamma. Then I also need a higher dimension version of K. Well, it's not really a higher dimension version of K. It's actually a higher dimension of a fibration of K over Sn, which actually appeared a number of times. So what it really is a higher dimension analog of the RV set that has been appearing from time to time. So so what do? I have my set Sn here. And for each lattice here, I can reduce it mod the maximal ideal, and I write that Vn. Vs, sorry. All right, and then if I take the collection of all of these things, I call that Tn. All right, so really what Tn is a n-dimensional, is a bundle over Sn of n-dimensional k-vector spaces. Okay, so you can show that essentially none of these things can be eliminated, and the good news is that at least in the simplest of all theories of valued fields, which is algebraically closed field, you don't have to go any further than that. So if you add points for, if you have the field sort and then you add points for all the lattices and then for all these points in these bundles, then you eliminate imaginaries in algebraically closed valued fields. So that's a theorem of Haskell-HrushovskiMacpherson. So what I want to do in this talk is consider other Henselian valued fields. And then what might happen is that, you have a residue field and you have a value group, and they might come with their own imaginaries. And there's no reason, if they're not eliminated in K, there's no good reason for them to be eliminated at all. So, so if we're in a general Henselian valued field, we'll have to deal with those. And so in the spirit of the Ax-Kochen-Ershov principle, one could say, we know that a valued field is essentially controlled by K and gamma, so let's conjecture that this is all we have to do. All right, so I said this is a very unreasonable hope because it is utterly false. Well, I mean, okay, at this level of generality, it cannot possibly be true because of a number of issues that I'm going to present now. So first of all, we have to deal with the cosets by nth powers. So maybe they're finite sets, and then they probably won't bother us too much. But maybe they're infinite, and then they're probably going to bother us a lot. And in fact, this problem is, and actually they might even have their own imaginaries that we have to deal with. So in fact, this problem is already known to happen in when you're trying to eliminate quantifiers, and we know a solution for that, which is use this RV thing I was talking about earlier, which is just T1. Right, so if we want to have any reasonable hope of a general theorem, we probably should be considering RVEQ, so that we also encode all of these groups, because it can be shown that they factor through this thing. Okay, second problem. It might happen that I have bad ideals around. So if I have a definable ideal, which is not a multiple of M or O, then I'm going to get into real trouble, because when I look at essentially what could be considered a generalized ball with this radius, then I won't have any idea how to encode them. Okay, so this set is really just the set of balls whose radius is I, and there is no good way to eliminate it. And so, well, in this talk at least, although there could be other solutions, in this talk I'm just going to try to make sure no such I exists, so that I can be, well, I can do what I want. So in particular, what I'll do is, so any of these ideals come from cuts in the value group, and so I'll just make sure that there are no bad cuts in the value group by asking that it's definably complete. So definable completeness means that any definable upper, with a bounded set has a supremum. Okay. And so in particular, you'll see that under this assumption, every ideal inside of O is either of the form, well, is a multiple of O or a multiple of M, depending on where the cut lies. Okay. Then there is another quite annoying problem, which is that, well, closed balls are extremely annoying. Because if you look at the set of open subballs of a closed ball, well, in general, you don't really know how to canonically interpret it. So it's a torsor of the residue field, of the additive group of the residue field, but it might not have a point. And so it might not be canonically isomorphic to the residue field, and so you really don't know anything about it. Right, so the problem is when it's empty, when it has no point over the ball, then its structure is completely, we can't say much about it. So one way to deal with these things is to actually also add them to the things we allow, which is that one of these things can be encoded in VS for well-chosenness, which is the usual trick of encoding torsors into vector spaces. And then their imaginaries are going to live in VSEQ for well-chosenness. Okay, so if I'm not mistaken, these are the main obstructions I know to the conjecture I stated earlier. So, well, I can try to formulate a better conjecture, which has a hope of being true. And so what I can do is the following. So, well, let me define the following set, which is, so if I take an element, so mg is going to be m with the geometric sorts. I think I defined g at some point, but I probably didn't stress it out. G in all this talk of Haskell-HrushovskiMacpherson, so this bunch of sorts. So yeah, so if you have a geometric element, then, well, a bunch of geometric elements, then you can define what's called the stable part, which is just the collection of those vector spaces over A. And then I'm going to define a set dA, which takes in account both things we want to know about, which is both the stable part, so these VS that might appear, and the RV that we need to solve the first problem. And so now that we have that, we can write a new conjecture. And so it's less legible because actually the set I encode in depends on the trace of E on the geometric sort. So it's less appealing than the previous one because it's a little more technical to state. But it has the incredible advantage of possibly being true. Okay, so what this says is that if I have an imaginary in some Henselian 0,0 field, and I look at the trace on the geometric sort, and I assume that, so actually, yes, I'm going to do more than just assume that it's definably complete, because that allows to solve other problems that I'm kind of hiding under the rug. So I'm actually going to assume that it's either divisible or a Z group, which implies in particular that it's definably complete. What is Z group? It's elementary equivalent to Z. well, then this imaginary is weakly coded in DAEQ, which means that there is a tuple in DAEQ which is algebraic over E, and E is definable over this thing. Okay, so it's a bit annoying because the set in which we're coding E depends on E itself, which is slightly annoying, but we'll see how to get around that eventually. Okay, so that's the conjecture that maybe one should be aiming for, and well, I'm not claiming in any way that I can get this far, but well, I can take care of some cases. Okay, so so now, after having told you a lot about imaginaries, what I'm going to do is tell you that actually that's not, I'm not going to at all consider definable sets, and what I want to really work with is definable types. Why? Because, well, actually, I want to work with types and not sets, and we'll see if they're definable or not. Why? Because, well, types are actually nicer to work with than sets because they're more precise in what you can do with them. And so you can show the following, that if you have a collection of zero interpretable sets to which you want to eliminate imaginaries, the only thing you have to do is, given any set, to find an invariant type which implies that set. And this invariant type should be invariant over the least possible things, which is the algebraic closure of the code of the set you're trying to encode. So it's very easy, if you know that, to prove weak elimination of imaginaries. It's a very straightforward automorphism argument. We're going to do a similar argument a little later on. Okay, there is a problem with that statement here, which is that in general, computing the canonical basis of an invariant type is hard, if not impossible. So probably you want to work with definable types instead, and one thing you might reasonably want to do is proceed in 2 steps. So first, for every definable set X, find, oh sorry, there should be an ACL EQ, there should be an ACL here, otherwise there is little hope of that ever being true. So you find a definable type over the algebraic closure of the code, which implies that particular set. And then, given any definable type, you try to prove that it actually has a canonical basis in the sorts you're interested in. Right? So you can split the problem into 2 distinct problems. This problem is really the only part where you really have to care about definable sets, and this really becomes a problem about types, which is the part I want to mostly talk about here. Although, not really, because, well, you'll see in a second. So, so let's now see if we can say anything about the definability of types in Henselian value fields. Once again, at this level of generality, there is no reason density of definable types should hold, because the residue field and the value group could be totally horrendous and have very, very few definable types, so there is no hope this should hold. So what we're going to aim for is find quantifier-free definable types. And also, I'm going to do something a little more general than what we've been doing so far, because, well, first I can, and second, it's actually going to be useful at some point, which is like that, as always, mostly enrichment on RV are completely transparent for what we're doing, and so I'm just going to allow myself more structure on RV if I want to. And so the first result that I want to talk about while not really talking about it, because it's not entirely, I mean, not everything has been worked out, is the following. So I stated it as a normal theorem. If you want, you can take it as a conjecture, whichever you want. I didn't state it as a conjecture because we have serious ideas of how to prove it, so it seemed a little weird to just conjecture it. But anyway, it's not entirely written up, and in particular, it's very possible that there are too few or too many hypotheses. Too many is not really a problem, I guess, but too few would be. And so what we're going to assume is a bunch of things on the value group and the residue field, which is that they're stably embedded, which is just this condition. I don't really want to talk about it, which to make sure that we can reasonably talk about the induced structure on them. And I want them to be algebraically bounded, which means that in the case of a field, it means that the model theoretic algebraic closure is inside the field algebraic closure. And in the case of a divisible, of an ordered abelian group, it means that the algebraic closure is inside the divisible hull of the group. Okay, And then let's also assume that gamma is definably complete to avoid the problems we were talking about earlier, where we might have balls that we don't really understand. And then I claim that first, so I'm going to do it backwards from what I said earlier. I claim that first, every quantifier-free definable type has a canonical basis in the geometric sorts. And secondly, I also claim that every definable type is consistent with a quantifier-free definable type over the algebraic closure of the code. So here the algebraic closure of the code is really taken in the Henselian field, whereas, but we're looking at types really that live in ACVF. And definability also means in the Henselian field. So let me quickly give ideas of how to prove these things, although, as I told you, not everything is written up. So if you look at the first statement, it's essentially proved by Johnson in his account on elimination of imaginaries in ACVF. He only states it for algebraically closed field, but you can look here. He really only ever uses that it's Henselian. And secondly, well, this is the more problematic part. This should be provable using a mix of existing arguments in 3 various settings. So arguments that appear in my paper on an existentially closed valued field with a derivation, and then a later paper by me and Samara Montenegro on pseudo-periodically closed fields. Anyway, so from now on, I'll just assume that this theorem holds, and you'll see a number of theorems that are also called almost theorems. It's mostly because of that thing which is not entirely known to be true. So if you assume that to be true, then most of the rest is, actually has proofs. Okay, good. So, so now, oh yes, let's go back to that statement, and let's look. What we have, so I pointed out that the best we can hope for when trying to find definable types is to find quantifier-free definable types. And so, conversely, the question is, well, how do we go from quantifier-free types to full types? And so actually, in Henselian characteristic 0,0 field, we essentially know how to do that because of the following. So this might seem like a slightly horrible statement, but it's just a rephrasing of the field quantifier elimination theorem. So what I'm saying here, so I'm saying that if I can find a bit of RVMA such that all of RVMA is definable of that, and then if I can, yes, and then the full type of A is implied by the quantifier-free type of A. And so I forgot to write that down. I think it's the first time it appears. So just to stop having to specify things all over the place, from now on, whenever I write 0, it will refer to the quantifier-free LDiv part. And when I write nothing, it will refer to the full T structure, so the full L structure. Yes, it's in K. K is the name of the valued field sort. Yes, so this is just an easy consequence of elimination of field quantifiers because, well, under this hypothesis, if you have 2 types realizing this and that, it's quite easy to see that they have essentially, well, that the RV have the same type, and all formulas can be factorized through RV, and so you get that they have the same type. So why do I want this row around? You're asking because, well, by what I wrote, if I allow pro-definable functions, I could just take rho to be everything, and then the statement would be a lot simpler. But it's because sometimes sometimes, and you'll see in a second, it's interesting to know that actually the RV is generated by very few points that you can control much better. Okay, so what is the case where things work very well? It's the following. So if you have A, which is generic in some ball B over M, and C is an element of BM, then you can check that the RV of MA is exactly in the definable closure of that. So why does that happen? Well, essentially, because you have two cases to consider. If you have your ball with your point, what is it, A, and your point C, and then you have two cases to consider. Either all the roots of P are outside, and then in that case, it's not very hard to see that RV of P of A is, well, actually, let me for a second assume that B is actually open to make my life easier. Then RV of PA is just, what is it? It's the product of all these things, but you can change A and C, and so it's RV, well, it's RV of PC. P, oh yes, so if these are the EI, P is the product of the X minus EI over I. And then the other case you have to deal with is you have A here, C here, and then all your roots are very close to C. So that's here where if you assume that B is open. If B is closed, you have another case to deal with, which is a bit more complicated than that I'm just going to hide under the rug, but you can also compute whatever you want. And so in that case, RV of PA is going to be RV of A minus C to the degree of P. Because each of those, the RV of each of those can be rewritten as A minus C. Okay. Okay, so moreover, if B is open, this map here does not depend on the choice of C inside of M, which is exactly the same drawing again. If I move C to another point of M, because A is generic over M, don't forget, it's going to be far from these points, and so the RV is going to be the same. And so let's reformulate that. It means that the germ of the function rho over the type A over M is actually in DCLB. So this function, so the function itself is not B-definable, but its germ over the type is, which is all we will ever need. Because now, if you look at what we have up there, this part here, so in that case, the type of A over M is just time generic in B, so this is B-definable, so in particular B invariant. This part here is B RV of M invariant, because, well, RV of M is fixed, and this is, the germ is fixed by B when we fix B. And so the full type is B RVM invariant. Okay, so that might be a little frightening to ask for something to be invariant over a class size set. So it's a set which is the size of the model. But remember, RV is stably embedded, so actually it works out pretty well. Okay, so essentially here I've quickly done the proof in the case where we have just an element which is generic in an open ball. And so what you do now is just, well, you check you can do it for closed balls also. And you can do it for intersections of balls. And then you fiber the whole thing, and you get that. Right, so you get that if you have, oh, and so now I'm going to assume I'm working with a model to make my life easier. So if you have a type A, which is n-definable for some submodel of M, then I can find a function whose germ is, oh no, well, it's even, I mean, I don't even need to talk about germs in this case. I can find a function that's actually definable over NA, such that we have the required RV inclusion. So in that, why do germs disappear here? It's because if you have a germ over a model, it actually has, there are points in the germ, in the class of the germ inside the model itself, and so you can just replace it by someone from N. So you can define the germ over N. Okay. Yes, so let me quickly explain where this result comes from. Well, as I told you, it comes from fibrating the previous argument. And so what you do is you take an A and a C. We're going to assume that A is going to be dealt with later, and now we're trying to talk about C over A. And so what we're trying to find is, oh, sorry, this should be rho of AC. Yes, it should be rho of AC. There should be a C here and a C there, I'm sorry. So we are trying to find a rho whose P germ is definable and such that this equality holds, and then we just do the induction. And so what I'm claiming is that this can be done in the following cases. So it can be done if C is generic in an open ball or a strict intersection of balls over MA. And this is exactly the argument I did down there. Except now you're not working over, well, you're working over a point that realizes a type in the universe, but this is not really a problem. You can also do it for closed balls, provided there is a canonical open subball, a maximal open subball inside of it. Because otherwise, so the argument I did to show that the germ was invariant doesn't at all work in a closed ball, because if you're generic in a closed ball, it doesn't mean that your RV to everything in that ball is constant. This is not true at all. And so you have to know that you have a canonical closed ball inside. And so it's to prove the existence of such canonical open subballs, of such canonical open subballs inside of closed balls that I need to be working over a basis which is a model up there. And finally, I can also do it if C is algebraic. So remember, here I'm cheating a little, because if C is algebraic over MA, since that type is n-definable, it's really algebraic over NA. OK, so this is probably this is the main technical result that's going to help us do everything else, which is that even for n-ary types, at least over models, we can complete them, at least we can compute their RV. But now, by similar arguments as before, we can show that, since we know how to compute the RV, and the RV is the only thing that's preventing us from having full quantifier, knowing the full type, we get that if I have a quantifier-free definable type over a model, then the type of A over M is actually n RVM invariant. All right, so now you're probably wondering, we've strayed very, very far from elimination of imaginaries, because, this n here is highly, I had to work over a model which is often not very canonical, and then I also have to deal with this RVN around. So let's see what we can get out of this thing. So let's assume that K is stably embedded. Actually, I probably need more hypotheses than that. I forgot that I added a lot of hypotheses. I also want the same hypothesis for gamma, I think, because that's what I used in the almost theorem. So I want the hypothesis of the almost theorem, and I think I did not copy all of them, so I also want gamma to be stably embedded and eliminating existing things. Oh no, actually, in the almost theorem, I even asked something stronger, which is that they were both algebraically bounded. So sorry, this is utterly false. And so you should replace it by K and gamma are stably embedded and algebraically bounded. And gamma is definably complete, and that I remembered to put. All right, so if we have that and we pick an E in MEQ, let's take A to be the geometric part of its code, and F be a zero definable function, and A in Km such that E is of the form FA. Then, by the almost theorem, I can find quantifier-free A definable quantifier-free type, which is consistent with the pre-image of E inside of my model. And so in fact, taking A to realize that type, I can assume that the quantifier-free type of A is A definable. So small a is big A definable. And so now, applying the corollary above, I get that the type of A, the full type of A, and hence the full type of E over M, is n RVM invariant for any choice of n between A and M. Okay, but remember that E is in M. So now I have an element of M that has an invariant type. So it's actually definable over whatever it's invariant above. Actually, so here I'm hiding the fact that I'm using that RV is stably embedded, to be fair. But it is, so we can. Okay? And so now that looks like an internality statement. It's not exactly an internality statement because, actually, this is exactly saying that E is internal to RVM over N. But we can do a little bit better than that because we know that it holds for any possible N. So by a compactness argument, we can show that there is an A definable set which is internal to RV and contains E. I forgot to say that. Yeah, little e should be big E. Otherwise, this is not very interesting. Okay, so we find an A definable set, big E, which is internal to RV and contains little e. Okay, so little e is not very far from being encoded in RV. It might need parameters in any model to do that, but it's not very far from being internal to RV. So what can we do now? Well, essentially we have two options. Yes? I mean, a set is internal to another set if there is a finite set such that so if there is a what is it? If there is a function from RV to E, a definable function with new parameters from RV to E, which is surjective. So it says that you have a bijection between E and RVEQ over some new parameters that you don't control. Okay? So, and the whole point now is to try to control those new parameters. And so there are two ways to do that that I'm going to talk about. The first is to essentially, so remember, well, essentially the reason we wanted a model was to deal with that case, to be able to find a canonical subball. So essentially what we have to deal with is closed balls. And so what we're going to do is assume that essentially we have no problem dealing with closed balls. So if we have a closed ball, either it isolates a complete type over anything it's defined of, or we can find actually a ball, we can find a maximal open subball inside of B. And so that is exactly going to tell us, well, I mean, it's going to tell us that we don't have any imaginaries in there unless we already have a point, and in which case, if we have a point, then it really lives inside K, which we already know how, inside the residue field, which we already know how to deal with. So that tells us that given any imaginary set of imaginary points, I can find a model containing its geometric part such that the type of that model over the geometric part implies the full type. Essentially, what you do is you just take, well, first you take you look at all the closed balls you have. Either they're complete type, so you just add the point in them, or they already have a closed subball and you don't deal with them. And then you do that for all open balls and you repeat until you have put points in every possible balls. And then you check that if you have put points in every possible balls, then not only do you contain GA, but you also Henselian, and then you also lift you lift RV, and then by Ax-Kochen-Ershov you get a submodel. So I mean it's a complicated induction, well, or it's rather straightforward but long induction on using what we've done earlier. And so once we know that, by stacking an invariant type on top of another invariant type, we get this. Oh, no, sorry. That's the next part of the argument, sorry. So once we know that, that's telling us that actually the points that I need here to witness internality can be taken to have a type over GA that implies its full type over A. And that's exactly going to tell us that we don't need them over A. And since A is the code of E, this is exactly going to tell us that any E can be encoded in there. Which, well, is better than my reasonable conjecture. And, but it uses a very strong assumption it's actually really an assumption on the residue field that is, well, so we'll see in a second. I know how to prove it essentially when the residue field is super simple of U rank 1. So it really needs to be very connected and one-dimensional. And so in particular, if it's a bounded PAC field, I can do it. So if K is a bounded PAC field, characteristic 0, then I can look at either K of T gamma or K of TQ, and they both eliminate imaginaries up to G. So here I'm hiding some more arguments, which is that in those two cases, I actually know what the imaginaries in RVEQ are, and so I can just get rid of them too. And so I get elimination up to G, provided you add constants to the residue field so that it eliminates imaginaries. So these are the constants that are needed to encode the Galois group. Okay. Well, maybe I should also have put that in orange because it depends on the normal theorem. But also, and I find that extremely cute. And this is essentially one of the reasons I wanted to allow arbitrary enrichment on RV. If you add an angular component, the result still holds. Because an angular component is just an enrichment of RV. And I find that quite cute because I don't think there is, even for ACVF, any known proof of elimination of imaginaries for ACVF with angular components. Okay, then I think this probably should be even in yellow or something like that, which is that I believe that, well, so if you take K, which is elementary equivalent to a finite extension of QP, this thing here is not true because it has subgroups, and so you could find things on, well, you could have a non-complete type around. But I think there is a statement that is strong enough to actually make everything work, but this statement is still to be found. I mean, I have reasonable ideas of what it is, but and then it should follow that if you have if you take K to be elementarily equivalent to a finite extension of QP, those two fields also eliminate imaginaries up to geometric sorts. Okay, good. So now, so I told you I had two solutions to deal with my problem that I had to go to a model at some point. So this is the other solution, which is that I'm going to use stably dominated types, which are exactly what are needed to lift the sets I need. And so, so I see I'm running out of time, so I'm going to go a little quicker. And so, so what you can show is that if you have a point which is generic in a closed ball, and you don't know that you have a point in it, then you can still compute RV, but you need to know about STA of M. So there is also a slightly weird assumption, because at some point I need to compute things in ACVF, and then I need to get them back down, which is exactly what this thing says. Okay, and by doing an induction on that case, you immediately get that you can find a model whose type is invariant over the stable part. No, so sorry, over the stable part and RV. So if you have an A, you can lift it to a model whose type is invariant over A and the stable part and RV. And so for you, by combining the two results, and not, it should be a normal theorem, I guess. Oh, no, this is a theorem because it's the local version, sorry. By combining the fact that over a model you know that you're invariant and you can find an invariant model, by putting one on top of the other, you see that if you're A definable, then in fact your type is ADA invariant. Okay, and so now if you apply the results that allow you to go from the local statements about types to the imaginary statements, so applying the first almost theorem, you see that that if you assume that K is stably embedded and algebraically bounded, oh, I remember to put the right hypothesis here. And gamma is pure divisible or a Z group. So why do I require more about gamma now? It's because I need to now ensure that, and this requires a little more hypothesis. Then any E in MEQ is weakly coded in DAEQ. So under this stronger hypothesis, the reasonable conjecture holds. Okay, so I hoped I would get there faster because I still have 5 slides to talk about. But if you know me and you've heard me talk, you probably see what's coming, which is that I really want to add operators. So what do I mean by a valid field with operators? Well, I'm just going to take a definition of a valid field with operator, which is kind of weird, which is I'm going to take the definition, which is exactly what I want in the end. And I don't care how the operators were built. I just want to know that there is a reasonable quantifier elimination result so that I have a good prolongation notion. So that the type, so I take one of my enriched Henselian fields, I add operators on top of it, and I ask that the type with operators follows from the type without operators applied to what should be the prolongation. So now I'll have more indices. So nothing is still going to talk about the Henselian enrich on RV, and then theta will refer to L theta structure, as one could guess. Okay, so oh yes, so this is totally easy. Remember, we have that theorem, but we know that we assume that the full type is controlled by this thing, and so we just apply the previous theorem to that thing, and we're done. So we get that if I have a set whose prolongation, the quantifier-free type of its prolongation is a definable, then the full type is a DAM invariant. And then, oh, well, yes, sorry. Now I can't use the almost theorem anymore to get to imaginaries, because the almost theorem only worked for things without operators. And so I need something else, but you can use theorems of mine and Pierre that works in the context of valued fields with operators. And so you can first show that, well, under certain assumptions, you can find a type which is consistent with anything definable in the Delta language. And then you can check that its canonical basis is also okay, provided you check that there are no weird cuts. Right? So if you have an externally L-definable subset of gamma in M, then which is also definable in the new language, then it has to be definable in the old language. So this is an hypothesis stating that there are no weird new cuts. So if you apply that theorem and you use that, okay, I'm not going to give an abstract statement. What I'm going to do in the last, well, 2 minutes, I guess, is quickly tell you that we can deduce things about this asymptotic theory of FP of T-alg with the Frobenius. So this theory already appeared, when was it? On Wednesday in Udit's talk, although he called it IVFA, but I'll call it GFA because that's how I've been calling it, but maybe I should change the name because, I don't know, we'll see. Yeah, so let's take VFA to be the existentially closed theory of valued field with an omega increasing automorphism, that is an automorphism that preserves the valuation and increases the valuation very much. And so we'll be working in the language where we add an automorphism, well, we have RV and we add sigma on both K and RV. And yes, it's VFA 0. Did I not? I forgot. Okay, yes, there should be an equicharacteristic 0 statement. Yeah, I'm only interested in equicharacteristic 0. And then by results of various people, well, I can build a model of that theory by taking a model of ACFA 0 and an omega increasing divisible ordered abelian group, and then just taking the Hahn series, and with a reasonable automorphism. But I can also do it by taking an ultra product of these structures. Okay. We also know that VFA 0 eliminates field quantifiers, so this is almost proved by Duran, but if you want the RV result, you actually have to look in the work of Powell. And K is stably embedded in a pure model of ACFA 0, and gamma is stably embedded in a pure model of omega Dirac. In particular, it's so minimal. So why do we care? Because remember, we had that weird hypothesis about not having new cuts. And so it turns out that there is a Kyoto minimal lemma that tells you, where am I? Yes, you have a Kyoto minimal lemma that tells you that if you have a no minimal enrichment of a minimal theory, this always happens. You don't have new weird cuts. And so if you apply that and all we've done before, you get that everything is coded in G and DA. Well, did I forget G here? Yeah, I very, very much forget G here. Oh no, I have A. Okay, it's okay, I have A. And I'm running out of time, so I will very quickly tell you that in fact we can also deal with this DA in this case. And we can probably understand its imaginaries by first understanding the structure on STA, which is super simple and itself eliminates imaginaries. And then you can add RV to prove that this structure also eliminates imaginaries, and then you get that VFA0 eliminates imaginaries up to G. But this uses stuff, well, this is not entirely done. I had one last slide about mixed characteristic that I'm just going to show up, but I think I'll stop here.